All right, so we're getting now into chapter 4. Chapter 4 is all about atoms and elements. And again, we're not doing all of this chapter. We are doing a subsection of it. So we're doing the first 5 sections. And actually in section 5, we're really only doing that first half of that section as well. So if you read on into chapter 4, some of the later sections get into things like periodic trends and how to evaluate the size of an atom and how big of an ion it's going to make and those kinds of things. And that's too far for us. We're gonna pull short of that. But our primary focus is going to be looking at elements, looking at kind of how the periodic table is made up, how it's arranged, and getting into the atom itself and looking at what is the atom made out of, how can I use that information to give me information about the atom itself and some of the properties that it might have. So if we look into section 1 here, section 1 is all about elements and symbols. And just to kind of recap what we talked about last week, an element is a pure substance where we only have one kind of atom present. So from a chemical compositional standpoint, elements cannot be broken down into simpler substances. They are the simplest pure substance that exists. And you will find lists of elements either in kind of these table forms here or inside of the front cover of your textbook. It has a periodic table and a list of the elements. Usually it's from A to Z. Although I'm not entirely sure because I've never actually held a copy of the physical textbook. Only thing I've ever seen is the ebook. But again, what we want to really focus on is these are pure substances, which means that they are chemical substances, chemical combinations, chemical fixed ratios in the cases of compounds, and we cannot break them down. They are as simple as pure substances get. Now, the naming of different elements actually has a very wide and varied history. There are a number of elements that are based in Latin and Latin roots. One of the common reasons for that is that, especially going back to the earliest days of science, Latin roots, Latin was the common language of the people, well, or at least of the scholar. If you go really far back, you start looking at, what we would call Christian church history, and the entirety of that church history is in Latin because of the Roman Empire and the fact that they spoke Latin in that historical era. So you get a lot of Latin kind of flavor in a lot of the elements, especially a lot of the early elements. You also get in some of that, plays and references to mythology, or simply to the origin of the substances themselves. So magnesium coming from the mineral magnesia. Getting uranium and titanium, which come directly from mythological beings, mythological creatures, ancient religions. Some having roots in Greek, because again, Greek, another common spoken ancient language. And then you get some that are just named for where they were discovered. Californium, berkelium, because it was discovered at the University of California at Berkeley. Tennessine, which isn't on that periodic table, but it is on the one I'm going to give you. which was discovered, you guessed it, in the state of Tennessee. And then there are those that are related to just great scientists. Curium wasn't discovered by the Curies, but it was named after them as a tribute to the work that they did toward chemistry and physics. Copernicum, same thing. Nicholas Copernicus, known for the Copernican model of planetary motion, physicist at his heart, astronomer, had nothing to do with the finding of Copernicum, but an element named for him as an homage to what he contributed to science. In addition to having names, elements are also given a chemical symbol. That chemical symbol is unique to a given element and has one of two forms. It is either a one-letter symbol or a two-letter symbol. The first letter in either type of symbol is always capitalized. If there is a second letter, that second letter has to be lowercase. How do we come up with these different kinds of symbols? Well, a lot of it has to do with generally the first element that is discovered with a particular letter usually gets a one-letter symbol. And then after that, we have to abbreviate based upon well-constructed, well-understood, easy ways of breaking down that particular name. Now, it's not always the case that it works out that way. For example, there is no letter L on the periodic table, but there are a number of L elements. They just all happen to be two-letter. But your one-letter symbols, these ones tend to be very common elements also. Hydrogen, carbon, nitrogen, oxygen. Two-letter symbols, again, for the most part, it kind of works out that it's the first two letters of the element's name, but it's not always that's the case. Sometimes it is. You got cobalt, calcium, aluminum. All three of those, the two-letter symbol matches the first two letters of the element's name. But it doesn't always work out that way. Magnesium is Mg instead of Ma. Chlorine is Cl instead of Ch. Why are we looking so deeply into some of these elements? Well, a lot of them have some really important applications and uses for us. Carbon, for example. Carbon's in pretty much everything. If it was ever living at one point in time, it has carbon in it. And carbon is one of those elements that shows up in a lot of places. And we talked about this a little bit, but just the idea that merely changing the form of the carbon can drastically change its properties as well. In graphite, having sheets of these rings, very flexible, very smooth. Those sheets are able to glide over one another very easily. That's what makes graphite a perfect material for pencils, because it's a soft solid that, because of that nature of how those sheets move over each other, it smears very easily. It marks very easily. It makes a great pencil. Diamond, the exact opposite. Super rigid, because every single one of those carbons is bound to 4 other carbons. And so you've got a rigidity in there that is unmatched in a lot of materials. And for that reason, diamond is so darn hard compared to other substances. And then you've got some other ones that are just kind of interesting. Buckminster fullerene, on the bottom left there. That is basically a spherical carbon. If you look closely, it's kind of hard to see, but if you look closely at the structure of it, what you'll see is that you basically have a 5-membered carbon ring surrounded by a series of 6-membered carbon rings. And that just repeats over and over and over again. If that looks familiar to you, that's because that's exactly how a soccer ball is constructed. On a soccer ball, you've got black pentagons surrounded by white hexagons. And they basically repeat each other over and over and over again until they create a spherical object. Now, Buckminster fullerenes are kind of cool, but where they get most commonly applied is we can take this technology that is used here, and that becomes the basis for what we call nanotubes. Carbon nanotubes make up a whole wing of material science called nanotechnology. Nanotechnology is responsible for a lot of things that are going on in our world right now, and have a lot of really cool applications as well. We're talking about things like drug delivery. We're talking about creating cages that can support certain types of materials being transported throughout the body and then released in a specific way when they get to a specific site. Lots of really cool stuff happens with nanotech. Another important element for us, mercury. Mercury, whose symbol is Hg. Hg coming from the Latin origin of mercury. Mercury is one of 2 elements that is liquid at room temperature naturally. The other one is bromine. So you've got one metallic liquid and one non-metallic liquid element. All the rest of the other metals are solids. All of the rest of the non-metals are either gases or very low melting solids. What's interesting about mercury is it's incredibly toxic. And to our bodies, you can put mercury into your system in all 3 modes of entry. So the primary modes of entry are inhalation, absorption through your skin, or ingestion. You eat something or drink something that has the toxic material in it. And mercury can enter through your body in any of those ways, which makes it kind of unique because most toxic materials will invade in one of the manners, or maybe 2, but rarely in all 3. What happens, why it's so dangerous? Mercury is a disruptor. So it reacts with the protein molecules that are in your body and ultimately disrupts your cellular function. Long-term exposure can lead to a variety of different ailments, including brain damage, kidney damage, mental disability, and retardation of developmental skills, and physical defects, physical developmental issues. So obviously, if you are introduced to a large dose of mercury in a very short period of time, fatality would be probably the most common side effect of that. But you can see that if you're introduced even to small amounts of mercury over a large period of time, that can have nasty effects on your body. So that's section one. Section one is just about elements and just kind of what the origins are, really trying to introduce you to symbols and names, because that's where we're going with it. In section two, we're going to start looking at the periodic table. And so I'm going to give you a copy of this table. And what I want you to do with it, obviously, hang on to it, keep it with you. But as I introduce different things to the table, things that you might want to write down or consider, go ahead and just write those things right on this table. Think of this as kind of your study periodic table that you'll use to help you do the homework, help you do the online quizzes, help you get ready for class. So you can see on this periodic table, there are 118 known chemical elements. And we arrange those elements into two different kinds of groupings. When we are talking about rows on the periodic table, we refer to those as periods. It is the periods, the rows, that make the periodic table, well, periodic. And it is the columns of the periodic table. We refer to those as either groups or families. These columns are what make the periodic arrangement what it is. How did we decide on 18 different columns? How did it end up that we had 7 rows? Well, it all comes down to when we're looking at those columns, we want to make sure that all of the elements in that given column have some things in common. Not so much in terms of what they look like, but more in terms of what they do. So if I look at the elements in the first column, that first column is known as the alkali metals. You don't need to write that down yet. We'll talk about it more depth in a second. But the alkali metals all have something in common. They all react vigorously with water. They all react vigorously with air. And as a result of those two things, we tend not to see those elements in their pure form very often. We tend to see them more in compound form because of their reactivity. So how did we end up with this arrangement? Well, this arrangement is what allowed those elements that have the similar kinds of chemical properties to be together in the same column. And so it gets down to more complicated matters than that. We have to begin talking about electrons and electron arrangements to really get a full understanding of just that. But in the short and sweet kind of condensed version, that's exactly what it is. Each column has some things in common, has some things that are common to all of them that define that column. And that's why we sometimes refer to them as families instead of just groups. So again, just highlighting groups and periods. Again, groups are the vertical columns. Periods are the horizontal rows. Now, within a given period, there's not a whole lot of common ground between the elements in a given period, other than we would say that they have the same number of energy levels in their electron state. So that's really the only thing that we would say that is common to them. So if I'm looking at period 4, I would see that the electrons in those atoms are arranged over 4 energy levels. And in period 3, they would be arranged over 3 energy levels. And in period 2, over 2 energy levels, and so on. The period number tells me how many energy levels are in that atom. So coming back to this part then, you can kind of see we've already done this. We already have the 4 different group names in there. Let's just take a quick look at each of those groups. So inside of the alkali metals, again, we're talking about primarily from lithium down to cesium. Hydrogen gets left off because, well, as a gas, it really doesn't have metallic properties. Francium gets left off because of its radioactivity. But what we see in these alkali metals is extreme reactivity. These are extremely reactive with water and air, and they rarely exist in their pure elemental form. We tend to find them most in compounds. So lithium oxide, lithium hydroxide, potassium oxide, potassium hydroxide, and similar. In the halogens, again, it's going to focus on these first 5 here. We do know that tennessine is a halogen. It does, we would assume, if it were not so radioactive, that it did disappear in a matter of nanoseconds. We would assume it had halogen-like properties based upon its position, but it doesn't. So it is left off of this list in particular. What we know about these, they are extremely reactive with metals and nonmetals. So much so that they won't even exist in their atomic form. If they've got nothing else to pair up with, they'll pair up with themselves and create what are called diatomic molecules. And if you remember from the activity last week, we saw that kind of firsthand. Why was the chlorine Cl2 instead of Cl? It's a halogen. And its reactivity as a halogen meant that if it was in nothing else but itself, it would react with itself so that it would reduce some of that instability that is natural to it. Reactivity comes from instability. more reactive something is, the more unstable it was in its prior form. Again, just looking at metals, nonmetals, metalloids. Okay, primary characteristics we associate with metals, we think of them as being shiny. We think of them as being ductile. Can anyone tell me what ductility is? Okay, yeah, that's actually a different property. Malleability is another one. It's flexibility, easy to break into sheets and pound out very, very thin. Ductility is all about wires. How easy can we pull that material into a wire? So metals tend to be very shiny. They tend to be ductile, meaning we can pull them into wires. That's what makes them good conductors of electricity. They also have good conductors of heat as well. Nonmetals, by comparison, they don't have the shininess. They don't have the flexibility. If I try to bend them or flex them, they just break. They're very brittle by comparison. They don't make good wires. They don't conduct very well. And so as a result, we tend not to think of them as conductors, but rather as insulators instead. Like I said, metalloids kind of fit in between. They kind of take from both piles. Metalloids are often shiny in their appearance, just like metals are. Metalloids often have some ability to conduct electricity, but not nearly as good as a metal can. What we tend to see with metalloids instead is the creation of semiconductors, where we can combine metalloid samples together and help electricity to travel better through the mixture than it would have through either of the samples on their own. Now, a semiconductor is not a full conductor of electricity, but it's what we would consider better. So I can use these two non-metallic materials and create something that maybe I couldn't in a metal for different reasons. Metals have their own problems with corrodability and oxidizing power and that kind of stuff. So maybe I don't want a metal conductor because I don't want it to be susceptible to this kind of chemical attack. But I can make a semiconductor that, no, it doesn't conduct electricity as well, but it does conduct electricity kind of well. And that can be enough for what I need it to do, plus having the insulating capabilities, the lack of chemical reactivity capabilities that we might see in a metal. So this chart kind of looks at, can I compare all three against each other? Metal versus non-metal versus metalloid. And what we see is that there are properties in the metalloid that are metallic and non-metallic. And then there are some properties that are truly in between. The density of a metalloid kind of fits between metal and non-metal. Melting point fits between metal and non-metal. And so you do have some advantages and disadvantages in each direction.